Welcome to the deep dive. Today, we're really getting into something massive, this huge global shift in how we generate power.
Yeah, it's fundamental. We're talking sustainability, but also, crucially, the financial side.
Exactly. The risk, power plants potentially becoming stranded assets, shutting down way too early, that's billions, maybe trillions at stake.
And that financial angle is exactly what our source tackles. For this deep dive, we're looking at a pretty comprehensive paper from 2017.
Okay, 2017. So the data is a little historical now, but the framework should still be relevant. What's the full title?
It's structural changes of global power generation capacity towards sustainability and the risk of stranded investments supported by a sustainability indicator. Bit of a mouthful.
Definitely. So what was its main goal, its mission back then?
Well, the idea was to create a simple tool, something quantifiable. They called it the Sustainability Indicator, or SI. And the point was to track how national power systems were actually doing, moving towards sustainability. They built this huge database of power plants active up to the end of 2014 to test it.
Right. So a benchmark. Let's unpack that SI then. If you want to track a shift this big, you need a clear metric. How did they actually calculate sustainability? What goes into the score?
It's based on weightings for the different types of power generation in the mix. The exact formula isn't the key thing. It's how they weighted each source. That's where the interesting stuff is.
All right, let's start with the obvious ones. What got top marks and what failed?
Okay, so renewable energy, that's hydro, solar PV, wind, biomass, the whole lot gets a full weighting of 100% sustainable in their model.
Makes sense.
And on the flip side, coal and nuclear power plants both got the maximum negative score. -1.
-1 for coal. Okay, we expect that. High emissions, heavy metals, low flexibility. But nuclear, grouping that with coal at -1, that feels like a statement. Nuclear is often pitched as low carbon, isn't it?
It absolutely is, and that's probably the most, let's say, debatable part of this paper's methodology. They do justify it, though.
How?
They list several things. Limited flexibility compared to other sources, high costs, proliferation risks, and the big one, the unsolved problem of long-term waste storage.
The waste issue.
Right. Plus, they argue that if you look at the whole life cycle, mining to decommissioning, nuclear actually has higher specific greenhouse gas emissions than solar, wind, or hydro.
Interesting. So it broadens the definition beyond just smokestack carbon, incorporating other risks.
Now,
What about the sources in the middle?
that's where it gets more nuanced. Natural gas gets a slightly positive score, plus 0.25.
Positive for fossil fuel. Why?
Yeah, they see it as a bridging technology, necessary for the transition period.
Okay.
It's got lower emissions than coal or oil, it's more efficient, and critically, it's flexible, which you need to balance renewables like wind and solar that aren't always on.
Right, the intermittency problem.
Exactly. And there's a forward-looking element, too. The infrastructure built for gas could potentially be repurposed later for renewable-based gases, like synthetic methane or hydrogen made from renewables, what they call power-to-gas, or PTG.
No, so the plus 0.25 reflects that future potential for conversion.
Precisely. Then there's oil that gets a negative score, minus 0.25.
Why negative if gas is positive? Oil plants can be flexible too.
They can, but oil has higher heavy metal pollution and more CO2 emissions compared to gas. So despite the flexibility, it ends up slightly on the negative side of the ledger in this specific metric.
Okay, that SI gives us a really clear, if maybe controversial, yardstick. Let's use it. End of 2014, the study's cutoff, global installed capacity was, over 6,100 gigawatts. Huge number. What was the overall global SI score then?
Well, despite all the talk about renewables starting up, the global SI for the total active capacity was still negative. Just barely, but negative, -2%.
-2%. So basically a wash. We were right on the edge. Why wasn't it positive by then? Renewables were growing, weren't they?
They were, but the sheer weight of the existing system was immense. At that point, coal and nuclear together still made up 37% of all active capacity worldwide.
37%.
Yeah, 31% coal, 6% nuclear. And since they both score -1, well, they dragged the average down significantly.
It's fascinating because we often think of right now, or maybe the last decade, as the peak of sustainable focus. But this study points out our grid used to be greener in some ways, didn't it?
That's one of the most surprising findings, actually. The highest SI score wasn't recent at all. It was found in the oldest power plants still running, the ones commissioned before the 1940s.
Really? What did they score?
They had an SI of plus 91%.
91%. Way back then. How?
Very simple, really.
Yeah.
93% of that old capacity was hydropower.
Hydro.
Exactly. long-lasting, reliable, and scores a perfect 1 in the SI metric. After that, the global SI just plummeted as we built out coal and later nuclear capacity during the big industrialization push.
So we kind of engineered our way out of sustainability for a while.
You could definitely say that. The SI hit its absolute lowest point, minus 30% in the 1980s.
Minus 30. Ouch.
Yeah, that was when coal was still huge. And nuclear renewables had roughly equal shares, around 23% each, but it wasn't enough to offset the coal. The good news, though, is that since that low point in the 80s, the SI has been climbing pretty steadily, almost linearly.
Okay, so that brings us closer to the study's present, the early 2010s. This must be where we see the acceleration kick in, right? What did the new power plants being built just before 2014 look like in terms of SI?
The acceleration is really clear in the data. For all the new capacity installed between 2010 and 2014, the average SI was already positive, plus 21%.
Okay, positive 21. That's a big jump from the overall minus 2.
It is. And if you zoom in even more, just on the plants commissioned in the year 2014 itself, the SI jumps again to plus 23%.
23% for new stuff in 2014. What was driving that?
Renewables. In 2014, fully half, 50% of all new global capacity added was renewable energy. Mostly solar PV, about 16%, and wind, about 17%. It really shows that exponential growth curve for non-hydro renewables starting to take hold.
That contrast is stark, isn't it? New stuff at plus 23%, the whole existing fleet at negative 2%. I assume this picture varied a lot by region, too.
Oh, absolutely. It wasn't happening uniformly everywhere. South America, for instance, scored the highest regional SI, a really impressive 62%, mostly thanks to having 64% renewable capacity, largely hydro.
62%, wow.
Yeah. But then you look at Northeast Asia, and it was the lowest, down at minus 26%. That was driven by having 57% of their capacity still reliant on coal and nuclear. So the risk profile varies hugely depending on where you look.
And that concentration of risk brings us right to the money issue. Stranded assets. Power plants are built to last for decades. What did this study find about the typical technical lifetimes based on plants that had actually been decommissioned?
Looking at the historical data of decommissioned plants, they found coal plants operated for an average of 40 years.
40 years for coal.
Right. Gas and oil plants had slightly shorter average lifetimes, around 34 years.
Okay, 40 years for coal. That's a long time. But climate targets, like the 2-degree goal, imply we might need near-zero emissions from the power sector by 2050. A coal plant built in, say, 2014 would expect to run until 2054. That creates a conflict, doesn't it?
That is precisely the problem. That's the ticking clock. The study explicitly warns that meeting that 2050 zero-emission target means about 300 gigawatts of coal capacity already built by the end of 2014 is at high risk of becoming stranded.
300 gigawatts?
Yeah. They simply might not be allowed to run their full intended lifespan if those climate goals are enforced seriously.
That's an enormous amount of capacity. It represents jobs, investments, communities. Where is that 300 gigaW risk located? Is it spread out?
No, it's highly concentrated.
Yeah.
The study found that 81% of that specific high-risk coal capacity was built in just 2 countries.
Okay.
China accounted for 59% of it, and India accounted for 22%.
Wow. China and India holding most of that immediate risk.
Exactly. And the paper strongly implies that any further investment in coal, especially there, carries an even higher, almost certain risk of stranding. It really shifts the problem from just technology to massive economic and political challenges.
Does the study suggest how these plants might be retired early? Policy mandates, market forces making them uneconomic.
It focuses more on the necessity driven by the climate target, implying that, yes, policy or market changes must happen. It does differentiate for gas and oil, though.
How so?
Their lifespans are a bit shorter, and crucially, they have that flexibility and the potential fuel switching option we talked about.
Right, the power to gas idea.
Yeah. So the paper suggests gas and oil plants built from 2016 onwards need to plan for a switch to carbon-neutral fuels like biomethane or synthetic fuels. Otherwise, they also risk stranding eventually. But the risk is seen as lower for gas because that technological path exists, at least in theory, to operate within a zero-emission future if the fuel source changes.
Okay, so fossil assets basically need a plan B involving new fuels, or they face early retirement. Given that upward trend in the SI score towards the end of the data, what did the study project for the future? Could we reach 100% sustainability?
They actually extrapolated 2 possible future scenarios based on the SI growth rates they'd observed since the 1990s low point.
Okay, what's the more cautious projection?
If you assume the SI continues to increase at the lower long-term average rate seen before things really accelerated, that was about 2.5% per year, then the global SI would reach 100% by the year 2046.
2046. That's still within reach for meeting mid-century climate goals. It implies a fully sustainable power system is possible in roughly 3 decades, just based on that slower historical trend.
Exactly. But remember, the rate of change was speeding up just before 2014.
Right. What if that faster rate continued?
Well, if you extrapolate using the much higher rate they saw between 2006 and 2014, which is a pretty rapid 5.9% increase per year, then a global SI of 100% could potentially be reached as early as 2028.
2028. That seems incredibly fast. I mean, does the study factor in the real-world friction? Like policy delays, grid upgrades, the sheer scale of manufacturing and deployment needed, commodity prices? That 5.9% rate feels optimistic.
The study's projections are mainly based on extrapolating the observed installation rates and the resulting SI trend.
Yeah.
It suggests that purely from a capacity build-out perspective, based on the momentum seen up to 2014, it was technically feasible.
I see.
They emphasized that the share of new renewables was rapidly outpacing the rate at which old fossil and nuclear plants were retiring. So if that continued, 2028 showed a scenario where the market transition, maybe driven by falling RE costs, was actually moving faster than policy could keep up.
So pulling it all together for our listeners, what's the main takeaway here? Even though the world's power grid was still slightly unsustainable overall back in 2014, according to this metric,
Right, SI of -2%.
the speed of change, that accelerating SI growth, suggested that getting to a nearly 100% sustainable system was potentially achievable within just a couple of decades.
Yeah, either by 2046 or maybe even 2028, depending on which growth rate you believed.
But the huge catch, the real challenge highlighted, wasn't necessarily building the new stuff fast enough, but dealing with the fallout from the old stuff, especially that 300 gigawatts of relatively new coal plants needing early retirement.
Exactly. Concentrated mainly in China and India. Managing that transition without major economic or social disruption is, well, that's the multi-trillion-dollar question.
It leads to an interesting final thought, actually, building on something you mentioned earlier about hydro.
Okay.
The study noted hydropower plants can last over 100 years because they get constantly refurbished and almost unlimited technical life.
Right. They're incredibly durable assets.
So what if we apply that logic to modern renewables? If wind and solar farms are consistently repowered, swapping out old turbines and panels for newer, better ones every 20, 30 years, but keeping the site in grid connection, could they also achieve a kind of unlimited technical lifetime?
That's a fascinating question. Would it mean renewables become permanent infrastructure fixtures, constantly upgraded, locking in their dominance for centuries? It certainly changes how we think about energy assets.
Something to ponder. Well, for anyone wanting to explore the original analysis and that SI metric in detail, the full title of the 2017 paper we discussed today was Structural Changes of Global Power Generation Capacity Towards Sustainability and the Risk of Stranded Investment Supported by a Sustainability Indicator.
It's a dense read, but worthwhile. Thanks for joining us for this deep dive.